Hello viewers, I am Dr. Mala Das Sharma, retired professor of St. Pius X Degree and PG College for Women, Hyderabad. Welcome to my channel Chemphilic. So let's start the 21st episode of Teaching Chemistry through Riddle. Do watch the video till the end and join me in this program by answering the viewer's question. So let's start riddle number 21. X is a technique for structural elucidation of organic compounds. Certain isotopes of elements with special characteristics are active for this technique. X is caused by a particular transition where absorption of a definite electromagnetic radiation occurs in presence of magnetic field. The energy difference between the two states for transition is a function of external magnetic field strength. So, this is riddle number 21. Now, let's see the questions. The primary question is, which technique is referred by X? The answer is nuclear magnetic resonance or NMR spectroscopy. Now let's see the other questions related to this riddle. Second question, what are the special characteristics for the isotopes which are active for X? Give two examples. Third question, which electromagnetic radiation used for this technique? Fourth question, under what situation the transition mentioned in the riddle occurs? So, principle of NMR spectroscopy. So, this riddle is framed to explain the principle of NMR spectroscopy part 1. Now, nuclei of some isotopes possess mechanical spin. What is that? That means the nucleus is rotating along its own axis, that is spinning nucleus. And the total angular momentum of this nucleus depends on the spin, which is known as spin number or nuclear spin quantum number, denoted by I, capital I. Now, each proton and neutron has their own spin or spin number. Okay. So, the spin number of the nucleus is the resultant. Spin number of the nucleus means I, which is denoted by I. Is the resultant of the spin of the proton and neutron. Okay. And this spin number or nuclear spin number, they may have values say half, 3 by 2, 0, 5 by 2, etc. depending on the atomic number and mass number. See, nucleus with odd atomic number or odd mass number are having this mechanical spin. That means they are the spinning nucleus. And these spinning nuclei are active for NMR spectroscopy. Whereas nuclei having even atomic number and even mass number, their spin number I is equal to 0. That means they don't have this spin quantum number. That means which is equal to 0. They are inactive in NMR spectroscopy. So, nuclei of some isotope possess mechanical spin. They have angular momentum, and the total angular momentum of a spinning nucleus depends on spin or spin number or nuclear spin quantum number I. Each proton and neutron has its own spin, and I is the resultant of this spin. As I told you, spin number I may have values 0, half, 1, 3 by 2, 5 by 2 depending on the mass number and atomic number. The nuclei composed of even number of proton and neutron have no net spin I is equal to 0. The isotopes with either odd mass number or odd atomic number possess a mechanical spin, and only such isotopes can exhibit a NMR spectrum. Now, we know that any charged particle, when it is moving, a magnetic field is generated. The nucleus is positively charged because protons are positively charged particles. So when nucleus is spinning, that means rotating along its axis, that means positive charge is rotating, so a magnetic field is generated. That means a magnetic dipole, north pole or south pole, or you can say magnetic moment is generated along its axis of rotation. So each nucleus can act as a tiny bar magnet. Then this, in absence of external magnetic field, these magnetic nucleus are orienting in random direction. So, since atomic nuclei have positive charge, spinning nuclei generates a magnetic dipole north and south pole along the axis of rotation. The spinning nucleus behaves like a tiny bar magnet. In absence of external magnetic field, magnetic nuclei are randomly oriented. Now, so what we have seen, in absence of any external magnetic field, these magnetic nuclei are randomly oriented. But as soon as you are applying the external magnetic field, then this magnetic nucleus, they can take any one of the definite number of orientation, which depends on the spin number. Suppose spin number is half, then this magnetic nuclei can take any one of the twice I plus 1 number of orientation, that means 2 into half plus 1, that means only 2 orientations. That means those magnetic nuclei can take any one of the 2 orientations, and that number of orientation is depending on the spin number. Okay, and number of orientation is twice I plus 1. Okay, so see, when a magnetic nucleus with spin number I is placed in a uniform magnetic field H0, its magnetic dipole or magnetic moment may assume any one of twice I plus 1 orientations with respect to the direction of applied magnetic field H0, and the system is said to be quantized. Important nuclei, proton and C13, I is equal to half. So, number of orientation twice I plus 1 is equal to 2. So, for these nuclei of proton or C13, in presence of external magnetic field, they can take only 2 orientation. One is along the external magnetic field, that means parallel to the direction of external magnetic field. Another is opposite to the direction of external magnetic field. That means nuclei, either they will be aligned to the external magnetic field or they will be just opposite to the external magnetic field. So, thus the magnetic dipole of the nuclei will be parallel or antiparallel to the applied magnetic field, that is with or against the applied magnetic field. Now, so what we have observed, that this magnetic nucleus, in absence of external magnetic field, they orient randomly. Their axis of magnetic moment can be oriented in a random direction. Okay, but as soon as you are applying this magnetic field, say I is equal to half, that means spin number is half, then there will be only 2 states, that means only 2 orientation of the magnetic nuclei are possible. Acha, in one orientation or in one state, that is the lower energy state. Lower energy state means this magnetic nuclei, that axis of magnetic moment of the magnetic nuclei will be parallel to this external magnetic field. This is the lower energy state, and this is also known as alpha state. And another state is higher energy state, also known as beta state, where the axis of magnetic moment is anti-parallel to the direction of with respect to the direction of external magnetic field. And the difference in energy between these two energy state, alpha state and beta state, this difference in energy, it depends on the external magnetic field strength. We'll see. So, the alignment with applied magnetic field is of lower energy and corresponds to alpha spin state plus up of the nucleus, and the alignment against the applied magnetic field is of higher energy and corresponds to beta spin state minus up of the nucleus. The energy difference delta E is the function of external magnetic field. We'll see this one. So, this energy difference between this alpha state and beta state is the function of external magnetic field strength. As you are increasing the magnetic field, this energy difference is also increasing. So, when the magnetic field strength is more, the nuclei will have, that means then the energy difference also will be more, delta E will be more. Then nuclei will have more tendency to remain in the lower energy state. So, to take it to the higher energy state, you have to apply, it has to absorb more energy. Now, see, energy required for a transition, delta E, is directly proportional to the strength of the applied magnetic field. Stronger the field, greater will be the tendency of the magnetic dipoles to remain aligned with it, and higher will be the energy required for transition. Now, coming to this precessing nucleus. So, what we have seen that nucleus is rotating along its own axis. Okay. Now, see, this is the nucleus. It is rotating along its own axis. This is the axis. And you have applied the external magnetic field. The direction of the magnetic field is this direction. That means the spinning axis of the nucleus is making an angle with the direction of the applied magnetic field. Now, and it is, nucleus is rotating around this own axis. Under this situation, that means in presence of this magnetic field, this nucleus experiences a force towards this direction. That means for taking this axis parallel to this external magnetic field. So, as this nucleus is experiencing a force towards this direction, or axis of magnetic moment of the nucleus is coming towards this direction of external magnetic field, or parallel to the direction of external magnetic field, this nucleus draws a circle. That means this motion of the nucleus draws a circle perpendicular to the direction of the applied magnetic field. Then the nucleus is precessing. See, if the axis of the nuclear magnet is not oriented exactly parallel or anti-parallel to the applied magnetic field, then there will be a certain force by the applied magnetic field to orient it. It tries to orient towards this direction. Now, coming to precessional frequency. Now, since the nucleus is spinning, the effect is that its rotational axis draws out a circle perpendicular to the applied field. That is, the nucleus starts precessing. This motion is known as the precessional motion. It is rotating around its own axis and it is coming to this direction, drawing out a circle. The nuclei align in such a way that their magnetic axis make an angle with the axis of the applied magnetic field. It will always make an angle, not exactly parallel from the beginning. Now, frequency of this precessional movement of the nuclei is known as the precessional frequency. Now coming to flipping of nucleus. Now this transition of nucleus from one spin state, that is lower spin state or alpha state if I is equal to half, lower spin state to higher spin state or upper spin state is known as the flipping. So the transition from one spin state of the precessing nucleus, one spin state to other of the precessing nucleus is called flipping. Now we'll see. So this is the alpha state. Okay, and nucleus is here. By absorbing the radiation, when it goes to beta state, that is the flipping. Now see, this is the ground state population in the lower energy state and higher energy state. Now by absorbing the radiation, which radiation I will tell you now. Now by absorbing the radiation, this nucleus is flipping from alpha state to beta state. That means now the population here, higher energy level is more than lower energy level in the excited state. So this is the flipping. The precessing proton absorbs energy from radio frequency source when the precessional frequency is same as that of the radio frequency. That means the nucleus is precessing when its precessional frequency is same as that of the radio frequency. Let me tell you one thing. For this flipping of the nucleus or in NMR spectroscopy, we use the radio waves. Okay. So, when this flipping occurs, when the precessional frequency of the nucleus is equal to this frequency of the radio waves or radio frequency, then only this flipping takes place. Otherwise, other way you can tell, when this energy difference between the alpha state and beta state is same as that of the energy of the radio waves, then only this flipping occurs. The precessing proton absorbs energy from radio frequency source when the precessional frequency is same as that of the radio frequency or the quantum energy of the radio frequency matches up the energy difference between the two energy state at the field strength H0. So, when this occurs, what occurs? The energy of the radio waves and the energy difference between the two states or frequency of the radio waves is same as that of the precessional frequency of the nucleus. Then they are said, then this nucleus and the radio frequency beam is said to be in resonance. Hence, it is termed as nuclear magnetic resonance or NMR. Now, generally in NMR spectroscopy, we keep that radio frequency constant. Okay, so already you have seen that in NMR you have to apply external magnetic field and the radiation absorbed is radio waves. So in NMR spectroscopy, we will keep the radio waves or radio frequency constant. We will change the magnetic field strength. So at a particular magnetic field strength, the energy of these radio waves become equal to that of the energy difference of the two states. That time resonance occurs and flipping takes place. All protons in a molecule do not absorb at the same magnetic field. I'll discuss it in the other part of this program. Effective field strength is different for different protons depending on the environment. Now, thus for a given radio frequency, different proton requires slightly different magnetic field to produce the same effective field which cause absorption. So, this is the first part of the principle of NMR spectroscopy. So, what we have observed that the nuclei of some isotopes have spin, and this spinning nucleus, they have the characteristics. What is the characteristics? they should have the either odd number of odd atomic number or odd mass number. And in NMR spectroscopy, you have to apply the external magnetic field. Okay? And in presence of the external magnetic field, these magnetic nuclei, they absorb the radio waves, and transition occurs from lower energy state to higher energy state under the condition of resonance. What is resonance? Resonance is this radio frequency will be equal to that of the precessional frequency of the nucleus, or energy of the radio waves will be equal to that of the energy difference between the two energy state. Then that's flipping occurs. So this is the principle. Now we see the answers of the remaining questions. Second question, what are the special characteristics for the isotopes which are active for X? Give 2 examples. Isotopes with either odd mass number or odd atomic number possess a mechanical spin. Those isotopes with mechanical spin are NMR active, say proton and C13. Third question, which electromagnetic radiation used for this technique? Answer is radio waves. Fourth question, under what situation the transition mentioned in the riddle occurs? Already I told you, when this frequency of the radio waves become equal to the precessional frequency in presence of the magnetic field, or the energy of the radio waves become equal to the energy difference between the two energy state of the nucleus, then that is called resonance, and under the condition of resonance, this transition or flipping of the nucleus occurs. So this is the end of this riddle number 21. Now we'll see what is viewer's question for this riddle. So today's question for the viewers, what is the nuclear spin quantum number of 12 carbon, that is carbon 12, 12C? Now mail your answer to this mail ID malachemphilic@gmail.com. While writing the mail, you have to give your name, your affiliation and place. Then you have to write answer of the viewer's question of riddle number 21. Then give the answer. Send your answer as early as possible. Time to time, I announce the name of the viewers who will give the correct answer. So, thank you.